Hi, we are from Group 5, Section 3 for the subject of BFC 25203 Numerical Methods, where our project title is Application of Numerical Mathematics in Civil Engineering. Now I'll pass on to one of my colleagues to start the presentation.
This is our group member for this project. Now, I would like to introduce you about numerical method. Numerical method are essential tools in civil engineering, providing practical solutions for complex problems that are difficult or impossible to solve analytically. These methods are widely applied across various subfields such as structural, geotechnical, environmental, and hydraulic engineering. So, techniques such as interpolation, numerical integration, and finite element method play a crucial role in converting theoretical knowledge into practical engineering application, ensuring safe, efficient, and sustainable infrastructure design. The problem for this project demonstrates the application of numerical method, specifically Lagrange interpolation in the context of hydraulic engineering. The project focused on monitoring water levels in Bintulu, Sarawak over 24 hours period from April 23 to April 24 in 2025. The water levels are classified into four categories. Normal is 3 meters, alert 9.65 meters, warning 10.15 meters, and danger 10.65 meters. During this time, water level were recorded at 6-hour interval. However, a key data point at 8 p.m. on April 23 is missing. The first objective of this problem is to create a problem by using existing data. Second, to estimate the missing water level using Lagrange interpolation. And third, to calculate the absolute error of the prediction.
Next, I will explain the literature review for our project. Solving differential equation is very important in science and engineering, but getting exact answer called analytical solution is often hard or not possible. So we use numerical method to find a approximate answer. According to Ibrahim 2023, two common methods are Euler method and Taylor series method. They are simple, but they have problem like Euler method is not very accurate for the interval. Taylor methods needs many derivatives which are hard to calculate. This method can also give error or unstable result. To fix this problem, our project looked at interpolation method like Lagrange interpolation. This uses no data points to build a polynomial that have estimate unknown values. They work well with data from simulation or experiments. According to Ibrahim 2022, using interpolation can give more accurate result, take less computing time, and help us better understand how solutions behave. Now, let's look at the Lagrange interpolation method. This technique generally a polynomial that passes exactly through a given set of data points. It's worked by combining special basic polynomial, each designed to be zero at all data points except one. This ensures the final polynomial fits every known function value perfectly, as noted by Moore in 2034. Lagrange interpolation is especially useful when the exact form of the function is unknown, difficult to find or too complex to handle directly. It allows us to estimate the function value at point between the known data smoothly and continuously. Because of this, it provides a good way to analyze the function behavior across its domain. This method has broad application in fields like computer graphics, engineering, physics, and importantly in solving differential equations numerically.
So, for our group, we have choose Lagrange interpolation method and absolute error method to solve our problem. Lagrange interpolation method is a numerical method that uses a polynomial to estimate unknown values based on known data points. It builds a single polynomial that passes exactly through all the given points. So in this project, we use three known data points to construct a second degree polynomial since the number of points minus 1 determines the polynomial's degree. After calculating the estimated value by using Lagrange method, the accuracy is checked by using absolute error method, where absolute error method is calculated by using the formula of exact value minus the approximate value. Now, let's go through the methodology used in this project. So first, we identified the objective, which was to estimate the water level at 8 a.m. on April 23rd in 2025. So firstly, to apply Lagrange interpolation, we needed data points surrounding the missing value. In this case, we had three known measurements, which is at 12 a.m., 6 a.m., and 12 p.m. on the same day. So to simplify the calculation, we converted all times value into numerical form using 12 a.m. was set as 0 hours, 6 a.m. becomes 6 hours, and 12 p.m. become 12 hours. So the unknown point at a.m. was converted to 8 hours. Using these time values and the corresponding water level data, we applied the Lagrange interpolation formula to estimate the water level at 8-hour mark. This approach was chosen because it's efficient for a small set of discrete data and avoids the need for solving equation or using other numerical methods like finite differences.
Next, we move to the calculation and result. Based on the question, firstly, we need to find the absolute error when the exact value at 9 a.m. is 9.36 meter. We used the Lagrange interpolation to estimate the approximate value. The formula used is the Lagrange polynomial. Pn of x equal to the sum of Li times Fi for I from 0 to n, where each L is calculated using the time data, x value, and the corresponding fx value. Now, we substitute the value into the Lagrange basic formula, and we will got L0 equal to minus 1 per 8, L1 equal to 3 per 4, and L2 equal to 3 per 8. Substituting this into the polynomial gives us the approximate value. P2 of 9 equal to negative 1 per 8 multiple with 8.94 plus 3 per 4 multiple with 9.32 plus 3 per 8 multiple with 9.52, and the answer is 9.38 meter. Finally, we calculated the absolute error. 9.36 minus 2, 9.38 equal to 0.02 meter. For part B, we estimate the missing value at 8 a.m. Again, using Lagrange interpolation. This time, x equal to 8. We calculate L not equal to negative 1 per 9, L1 equal to 8 per 9, and L2 equal to 2 per 9. P2 of 8 equal to negative 1 per 9 multiplied with 8.94 plus 8 per 9 multiplied with 9.32 plus 2 per 9 multiplied with 9.52, and the answer is 9.33 meter. To estimate missing water level data, we use interpolation, specifically the Lagrange interpolation method, which is well suited for small, uneven time series dataset. For example, the water level at 8 a.m. on 23rd April is missing. Using known data point at time 0, 6, and 12 hours with corresponding water level at 8.94, 9.23, and 9.52 meter, we can apply the Lagrange formula to estimate the missing value. This method also allows us to estimate the value at 9 a.m. using x equal to 9. Once the estimated value are obtained, we can compare them to define water level categories such as normal at 3 meters and alert at 9.65 meters. This comparison helps us determine whether the situation requires further action or warning. If the actual value later become available, we can calculate the absolute error using the formula, the absolute difference between the exact and the approximate value. This helps in evaluating the accuracy of our interpolation approach.
For discussion, the result obtained from the application of Lagrange interpolation method demonstrate that it is a practical and accurate technique for estimating missing values in environmental dataset, particularly when the available data are limited and spaced at regular interval. In this case, the estimated water level at 8 p.m. and 942 meters, which is just below the alert threshold level of 9.65 meters. This estimation provides valuable insight into the behavior of the water level during the period question, especially considering the trend of increasing values from midnight to noon on April 23. The gradual rise in water level suggests a possible escalation toward more critical flood warning stages later in the day, which would be crucial for early response and mitigation planning. The small absolute error observed in the ventilation at 9 am further support the effectiveness of the Lagrange method, indicating that the polynomial closely followed the actual behavior of the data recorded. This implies that in situations where real-time readings are incomplete or interrupted, interpolation can offer a dependable alternative for maintaining continuous monitoring and decision-making. In conclusion, the project successfully utilized the Lagrange interpolation method to estimate a missing water level reading based on known values at nearby time point. The method provides to be both efficient and accurate as demonstrated by the minimal error in the ventilation process. The estimate value at 8 am provided useful information for the understanding the development of water level throughout the day, helping to determine whether the conditions were approaching critical threshold. This not only fulfilled the objective of the estimating the missing data point, but also highlighted the potential of numerical method in supporting engineering decision where real-time data might be incomplete. The finding of this project reinforced the importance of interpolation technique in civil and hydraulic engineering, particularly in applications related to flood monitoring, where timely and accurate data is essential for public safety and infrastructure planning. Therefore, Lagrange interpolation stands out as a reliable tool for estimating unknown values within a discrete dataset, especially in time-sensitive scenarios. Are you missing value? Because I use Lagrange interpolation just to estimate how perfect you are. So that's all from us. Thank you.